double integrals over general regions. Let's start with an example. Suppose that we want to evaluate the double integral over d of x plus 2y dA, where d is the region bounded by y equals 2x squared and y equals 1 plus x squared. I have this region shaded in the picture. Now recall that my function is z equals x plus 2y. And imagine that being a surface above the xy plane. Now it could cut through and go below, but for the sake of simplicity, imagine z as a surface above the xy plane or coming out of your screen. Evaluating double integrals over general regions is very similar, really not much more difficult than evaluating double integrals over rectangular regions. So let's see how to do this. Let's put our double integral down. And I'll put x plus 2y back in here. Now I have not decided yet which variable I want to integrate with respect to first. So I'm going to get a little bit more information. Let me put in the graph the intersection points. It's pretty easy to see that these graphs intersect when x is -1 and 1. And I could find the y intersection points pretty easily as well. It's going to be 2 on both those, but I think this lends itself pretty well to integrating with respect to y first, or really to x second. So recall that dx on the outside means that's the second integral. dy on the inside is the first integral. Now we need to integrate from which y to which y. Well, taking a random x value, notice that we're going to integrate from the lower y, which is going to be 2x squared, to the upper y, which is going to be 1 plus x squared. So now we have our limits, and we can integrate, just like we've been doing before, which we do in the following way. We're going to leave the outer integral alone, and then we're going to integrate this part with respect to y. So x with respect to y is xy, because x is treated as a constant. And then plus the integral of 2y is y squared. And we'll integrate from y equals 2x squared to y equals 1 plus x squared. And then dx. So it's going to be messier than integrating over a rectangular region, because there are some extra functions to deal with. But the idea is really not that much more difficult. Let's continue on. Leave my outer integral, -1 to 1. And then we're going to plug in the top limit for y. So we're going to have x times 1 plus x squared plus y squared, that is 1 plus x squared squared. And then we're going to subtract off the lower limit, minus plugging in 2x squared for y is going to give us 2x cubed, plus plugging in 2x squared for y squared is going to give us 4x to the fourth. And now we're going to do a little bit of algebra to solve this one, but the main calculus part, the setting up, the difficult part, I would say, is finished. But let's continue on. -1 to 1 of the following: x plus x cubed plus. Now we're going to multiply this out. It's going to give us 1 plus 2x squared plus x to the fourth. Then minus 2x cubed minus 4x to the fourth and dx. Let's see if we can simplify this a little bit before we integrate. Putting all our like terms together, we get 1 plus x plus 2x squared minus 1x cubed minus 3x to the fourth dx. And now we integrate this one with respect to x. And that will give us x plus x squared over 2 plus 2x cubed over 3 minus x to the fourth over 4 minus 3x to the fifth over 5 from -1 to 1. Plugging in the top limit, then plugging in the bottom limit and subtracting. I will let you do that on your own because that is not the purpose of this video. I assume you can plug in 1 for x and -1 for x. And just so you can check yourself, when you go through, your answer will be 32 over 15. But let's look at another problem. Let's find the volume of the solid that lies beneath z equals x squared plus y squared. So I drew that over here on the right. And above the region D in the xy plane, so I drew it here and then I redrew it on the right as well, where D is the region bounded by y equals 2x and y equals x squared. So how can we find this volume? Well, let's do our double integral of x squared plus y squared. I'm going to find some intersection points. We have the point 0, 0, and the other intersection point is the point 2, 4. And I think I'll integrate with respect to y first again, so that I can go from y to y to y each time, and then at the end add up all of those columns from x equals 0 to x equals 2. So what is y going from? Well, it's going from x squared and going to 2x. Now that we have the setup, we can integrate. Let's integrate with respect to y first, and let's be careful. We have 0 to 2, and then integral of x squared with respect to y is going to be x squared y. The integral of y squared with respect to y is y cubed over 3. And then from x squared to 2x. And finally dx. Let's plug in 2x for each y. So we're going to get x squared times 2x plus 2x quantity cubed over 3 minus, now let's plug in our lower limit for y, x squared times x squared, and then plus, but I'm distributing the negative sign here. Actually, I'll go and write it with my parentheses, plus, and then plug in x squared into y, we get x to the 6th over 3, and then dx. And then I'll set this up. I may not solve this one, but I could put these two things together. That would be 6/3 plus 8/3 x cubed, right? So we have 14/3 x cubed. So 14/3 when we integrate x to the 4th over 4. Then minus x to the 5th over 5 plus x to the 7th over 3 times 7 from 0 to 2. Or if I simplify this, 7/6 x to the 4th minus x to the 5th over 5 plus x to the 7th over 21. From 0 to 2, plugging in the top limit, we get 7/6 times 2 to the 4th, or 16, minus 2 to the 5th, or 32 over 5, plus x to the 7th, which is 128 over 21, minus, plug in the lower limit, 0. And if we were to put this together, we would get 216 over 35. One last example. Let's evaluate the double integral from 0 to 1, then x to 1 of sine y squared dy dx. So we're going to integrate with respect to y first. So the integral of sine of y squared with respect to y is, what is the integral of sine of y squared with respect to y? Now I know how to integrate the sine squared of y, and I know how to integrate y times the sine of y squared, but how do we do this one? Well, I'm not really sure. So let's do something else. What I end up with is an integrand that's either impossible to solve or really difficult to solve, or maybe we just don't have the techniques yet. But what if we were to draw this region and then change the order of integration? All right, so what region should I draw? Well, because y is on the inside here, I know that's y equals x to y equals 1. So I should draw the line y equals x. And this is saying I'm starting at y equals x, and we're going up to y equals 1. So here's one representative column. And then we're starting at x equals 0 and going to x equals 1. So the region in question is this one up here. So how can we write this double integral if we change the order of integration? We'll do dx then dy. Well, going horizontally, I'm going to draw a representative row here. That says we're going to go from x equals 0 to x equals y. And then y is going to go from 0 to 1. Does this help us? Well, let's see. I'll put the outer integral from 0 to 1. And now we're going to integrate this with respect to x, which means sine of y squared is a constant. So we have x times sine of y squared. From 0 to y, and then dy. Plugging in y for x, we get y times the sine of y squared. Plugging in 0 for x, we get 0, so minus 0, and then dy. And now I have an integral that I know how to do. I've done stuff like this many times. I know that this integral is a u substitution, where u is y squared, and du would be 2y dy. So I need a 2 out here to fix it, and then 1/2 as well. So this is going to give me 1/2 the integral from, let's see, when y is 0, u is still 0, 0 squared. When y is 1, u is 1 squared. So that doesn't change. So I have 1/2 the integral sine u du. Then I have 1/2 times negative cosine of u from 0 to 1, which will be negative 1/2 times the cosine of 1 minus the cosine of 0, which is 1. So we're going to get negative 1/2 times the cosine of 1 minus 1. And you can rearrange that as you desire.